Assalamu alaikum. This is Hamas Amir, and today Fida and I will be presenting YOLO algorithm, a real-time object detector. What is object detection? It basically consists of 2 points: classify the object and get the boxes around the object. Now what does it mean? In object detection, you simply place boxes around the object in the image and classify the object. So humans do object detection very easily. However, this is something computers have struggled historically for a very long time. Recently, a lot of advancement has been made to make detections more accurate. However, object detection is pretty slow. Let's make a comparison. A couple of years ago, RCNN came out and offered a huge boost in accuracy when compared to previous models, but processing time increased to about 20 seconds per image, as you can see in second row, third column. We needed a somewhat faster object detector to be able to use it for real-time object detection like in self-driving cars. Hence, YOLO algorithm was introduced in 2015. YOLO is the state-of-the-art object detection algorithm, and it is so fast that it has become a standard way of detecting objects in the field of computer vision. YOLO runs in actually more than real time at 45 frames per second or 22 milliseconds per image, which is a huge improvement over RCNN, and it has outperformed all the previous object detectors. However, its speed comes in at a little bit of price in terms of accuracy, as mean average precision, that is MAP, is reduced to 69%. Deformable. So why is YOLO faster than the previous object detectors? Deformable part model and RCNN, both of these methods were using a region-based classifier, and they are looking at an image thousands or hundreds of thousands of times to perform detection. What we really wanted was one neural network that could just perform a detection in a single pass when given the image. So advantage of this is that instead of looking at a network thousands of times with YOLO, you only look once, as the name suggests, at an image to perform the full detection pipeline. Now, Fida will continue onwards and will tell you more about the methodology.
So now we will try to understand what is object detection. Before diving into object detection, let's first understand the working of image classification and localization, since object detection is doing just that but on a larger scale. In image classification, we want to predict what's in the image. So we will train a CNN and it will predict the object present in the image, in this case, a car. While in localization, along with classifying the object, we are also predicting the position of the bounding box, such that the entire object, in this case a car, is enclosed in it. So let's now talk about how exactly can we get the bounding box and how to interpret them. So once the image is fed to a pre-trained neural network, it will predict a vector like this, where PC is the probability that image contains any class that the model has been trained on, Bx and By are the coordinates of the center of the box, while Bh and Bw is the height and width of the bounding box. C1, C2 and C3 are three separate classes which we are detecting in this case. In an application of self-driving car, we can define C1 as the probability that image contains a light, while C2 as the probability that image contains a car, and C3 as the probability that image contains a pedestrian. In this particular case, C2 is 1 while others are 0, which means the model has detected a car. We will obtain a final vector of size 1 by 8 in this example. However, this only works for a single object. Object detection will be done if there are multiple objects in an image, and one of the most popular algorithms for object detection is YOLO. Let's now look at how YOLO works. So what YOLO does is that it will overlay a grid on top of that image, and each cell in the grid will be responsible for predicting some bounding boxes. We will apply the concept of localization in each of these grid cells. We will take the center of the object and in whichever grid that center falls will be responsible for detecting that object. So let's say the center of this dog falls in this grid cell. So it will be responsible for predicting the dog. Now there might be some grid cells that don't have any object on them, like the one in the bottom right, but it is still going to predict some bounding box. We don't care what they are, we just want their confidence values to be very low. The output vector by such grid cells will be similar to this vector. So now we can train a neural network to classify the object as well as obtain the bounding boxes. We can take plenty of images, and for each of these images, since it is a supervised learning problem, we need to give their respective bounding boxes. Using the images and their bounding boxes, you can now train a neural network. The model will have 24 convolutional layers while 2 fully connected layers. We can use stochastic gradient descent and extensive data augmentation techniques to improve the model generalizability. Once the model is trained, we will then evaluate the model on unseen data using metrics such as mean average precision, which ranges from 0 to 100, and higher values are typically better. Before finalizing the model, we need to address the issue of detection of multiple bounding boxes for a given object. So let's say for a person, the model detected this yellow box, this red box, and this green box. And we know by visual observation that this green box is the most accurate one, since the entire person is enclosed in it, and the model also gave a class probability of 96%. We will use a concept of intersection over union to filter out the unwanted boxes, which for this case is the yellow box and this red box. We basically take the green box and we will compute the overlapping area of it using IOU with the remaining boxes. So if two boxes are overlapping more, the value of IOU will be higher. In our case, IOU of the green box will be higher with this yellow box and this red box. Hence we will discard them. We will filter out the unwanted boxes on the dog similarly. Finally, we will obtain an image with only one detection per object. This technique is called non-mix suppression. So let's summarize the working of YOLO. Firstly, we will train the model using a dataset of images and bounding boxes. Then we will evaluate the model on unseen images. Then we will give our desired image to a trained model for detection. And then we can get rid of the boxes with confidence value of less than 0.5, since it does not contain any object. Lastly, we will apply non-mix suppression to discard unwanted bounding boxes and obtain only one detection per object.
Guess who's back with some more information regarding the performance of object detectors? In practice, the system works well. It works across a variety of natural images. You can see it makes some mistakes thinking that the person in the bottom image is an airplane. What is generalizability? We also found some important properties of YOLO algorithm. It generalizes well on new domains. We trained on natural images and then ran it on artwork, and it still manages to detect all of the objects despite changes in textures. YOLO outperformed all the previous object detectors in terms of its generalizing capabilities, making it ideal for applications that rely on fast, robust object detection. Lastly, I would like to point out some of the applications of object detection. One of the best examples of why you need object detection for autonomous driving is in order for a car to decide what to do in next step, whether accelerate, apply brakes, or turn. It needs to know where all the objects are around the car and what those objects are that requires object detection. To sum up, this presentation contains many advantages and limitations regarding one of the most popular object detection methods, YOLO. This method can be brought into use more often in vast applications such as deep learning, self-driving cars, and real-time object detections with certain improvements, and it can become the most effective and widely used method. Thank you for listening patiently. Allah Hafiz.